Hello everybody. Today we'll talk about what is a tin can telephone. So to begin with, a quick introduction on what is a waveguide. A waveguide is a structure that guides waves by restricting the transmission of energy to one direction. Now, if there were no waveguide to begin with, sound waves would simply expand into 3D space. So in order to ensure that the waves travel only along one direction or along one dimension, we need a waveguide. So there are different types of waveguides for different types of waves. Examples include radio frequency waveguides, optical, and even acoustic waveguides. Examples of radio frequency waveguides include microwave oven, radar. In case of optical waveguides, there's this well-known fiber optic cable offering high-speed internet. And finally, we also have acoustic waveguides. Examples include horn, megaphone, loudspeaker, and even tin can telephone. So what is a tin can telephone? Well, a tin can telephone is an acoustic speech transmitting device made up of two tin cans or even paper cups connected together rigidly by a string. A tin can telephone is a purely mechanical device because it doesn't need any electricity to work. So it's a simple DIY project. For example, all you need is two tin cans and punch a hole at the bottom of those cans, connect them together by a string, and there you have a tin can telephone. So let's talk about a brief bit of history. So before the invention of electromagnetic telephone, mechanical acoustic devices such as a tin can telephone were used for transmitting speech and music over great distances. By great distances, I don't mean kilometers of distances, but maybe meters of distances. So from the year 1664 to 65, British physicist Robert Hooke experimented with sound transmission through a taut extended wire. Now, back in the day, the tin can telephone, or the commercial version of tin can telephones, were also referred to as acoustic telephones. So these devices were in use for a short period of time, while like Alexander Graham Bell's telephone patent was still active. Now, the reason why, because these devices served as a niche competitor because they didn't fall within the scope of Graham Bell's patent protection. But after Bell's patent expired, dozens of telephone companies flooded the market, so acoustic telephone manufacturers couldn't keep up with the competition and they went out of business. So they became obsolete. The maximum working range of acoustic telephones was limited, so about 800 meters or more under ideal conditions. So let's talk about the working principle of a simple tin can telephone. So let's say there is a tin can telephone and there are two people on either sides, A and B, and they want to communicate with each other. So person A pulls the string and starts speaking into can. So this is really important to pull the string because there has to be some tension in the string. So the person A starts speaking, the sound waves travel from the person's mouth and they go into the can and they hit the bottom of the can. Now the bottom of the can acts like a vibrating membrane or a diaphragm as in a speaker, and it starts vibrating back and forth. Now the sound waves hit this membrane, it sets into a vibratory motion. Now here the string is connected to the bottom of the can, so the vibratory motion from the diaphragm or the bottom of the can is transferred to the string. So these vibrations or the sound vibrations through air are now traveling through another medium, which is the string. So they travel through this medium as longitudinal mechanical vibrations. We call them mechanical vibrations, but at the end of the day, they are still sound waves traveling through a different medium, which is the string. And then finally, when the vibrations to the string reach the other end of the can, and the same process occurs where the energy is transferred from the string to the bottom of the can, and the bottom of the can starts vibrating again, recreating the original sound waves, which is heard by person B. Now let's perform an experiment. Let's calculate the time taken by sound to travel from person A to person B. Let's say they are separated by a distance of 2 meters and they're using a tin can telephone. The material of the string is nylon. We're assuming that's because the material properties are readily available, such as Young's modulus, Poisson's ratio, and density. And in the second case, let's assume that there is no tin can telephone to begin with. Person A and B are still speaking to each other just through air as we do in everyday life. So let's see which of these is more efficient. So to calculate the speed of sound in nylon, we need an equation. So as you can see in the screen, the speed of sound in solids is dependent on the Young's modulus, density, and Poisson's ratio. So the Young's modulus of nylon is 2.7 gigapascal. The density of nylon is around 1150 kilogram per meter cube, and the Poisson's ratio for nylon is approximately 0.39. So when we plug in all the values, you get the speed of sound in nylon to be 2164 meter per second, which is pretty fast compared to the speed of sound in air, which is only 340 meter per second. So now we know the speed of sound in nylon and air. The distance is fixed between two people, which is 2 meters. Let's calculate the time taken for the sound to travel from person A to person B. In the first case, let's assume that person A and B are using a tin can telephone and they are speaking through the tin can telephone, the material of the string being nylon. The time taken for sound to travel from A to B would be a bit less than 1 millisecond. And in the second case, let's say the person A and B are not using any tin can telephone at all. The time taken for sound to travel from A to B would be around 6 milliseconds. So you see here that sound travels 6 times faster in nylon than in air. Also, that is evident in the time taken, which is 6 times less in nylon compared to air. So it is more efficient to use a tin can telephone to communicate between two people than it is to speak merely through air, as per the calculations we see here. Now let's apply these calculations to a more real-world scenario, for example, as in case of acoustic telephones, which did work on the exact same principle of tin can telephones, but they were like the commercial versions of tin can telephones. So let's say there are two people in a town who are separated by a distance of 800 meters, and they're communicating through an acoustic telephone. The material of the string is obviously not nylon, but it is a galvanized metal, for example, steel. Let's assume it is steel and the speed of sound steel is around 5,900 meter per second, and the distance is 800 meters. If you plug in the value, the time taken for sound to travel is only 0.13 second. Now, back in the day, it was amazing that two people at a distance of 800 meters could communicate in less than 0.1 or around 0.1 second. We cannot imagine two people 800 meters apart communicating through air. Is just not possible. And all this for free because acoustic telephones don't need electricity to work. So the advantages include the string of the tin can telephone acts as a waveguide, so it transmits sound waves more effectively than speaking through air because waves travel only along one direction in case of a waveguide, whereas air is not a waveguide because there's no restriction for sound to travel along one dimension or one direction. It spreads out in 3 dimensions, so it's not efficient. And sound waves travel faster through a solid material, for example, nylon or steel, as we see through the calculations compared to air. Above all, a tin can telephone doesn't need any electricity to work. So, thank you for watching this video. I hope you enjoyed it. Have a great day.